Hey, you guys, here we are again. Another day off of school. Hopefully, you're enjoying yourself and you're having time to do some fun things that you like to do, but that you're also getting some rest to gear up for more AP chemistry. So, here we go today with photoelectron spectroscopy. And oftentimes, I put on there also known as PES. It's really common for chemists to realize that PES is photoelectron spectroscopy. So that is definitely an acronym that you can use freely. First off, I want to show you how this actually works. And so I think it's super important for you guys to understand how we get this data. Obviously, we don't have the tools to do this, but if you go on further, if you choose to go deep into chemistry in college, you can be running these types of experiments and you can be using this type of machinery. So this is one thing that in these experiments we have high energy photons. And if you're not for sure what photons really are simply energy, and they're on the electromagnetic spectrum. It's not visible light energy. It's higher energy than visible light, but we throw that energy basically in this machine. It's that energy is thrown at atoms, and so those photons then remove electrons from any shell. And that's important to realize in this. It's not just the valence electrons, it's the inner core electrons, and that's why it has to be super high energy. And then we're trying to measure the energy output. So what happens is the kinetic energy of these ejected electrons is determined. So remember, kinetic energy is basically your energy of motion. And so the frequency of these photons is recorded also. So we're able to calculate the ionization energy. And that's how we actually get ionization energies of electrons, is we actually have to pull the atom apart, and we figure out how much energy it took to actually pull those atoms apart. So the equation you see at the bottom is ionization energy equals, and that H is Planck's constant, and we will use that later on in this semester, but it's a constant that's used especially with wavelength, frequency, and like energy, motion, and light. The V is frequency, and then we subtract the kinetic energy from that to determine the ionization energy. Now, do we have to use that equation right now? No. So we don't have to worry about actually calculating it. We're just looking at the ionization energies that have already been calculated. So let's take a look at those. And here's some ionization energies. Now note, this is in megajoules per mole, which is even higher than kilojoules. And it's like another thousandth higher than kilojoules. And so I want you to take a look at, and I'm going to kind of circle some main ones that I find interesting to point out to you. So let me get my pen going on here. So in particular, I want you to look at sodium. And so if you look at sodium here, let me find, okay. You'll notice that the 3s has a much lower ionization energy than those inner core electrons. Now let's think about the actual electron configuration of this. Let's see where I'm at here. So I have 1s2 for sodium, 2s2, 2p6, and 3s1. So if you think about this, that 3s1 is going to be relatively easy to remove. And then as you get closer to the core and closer to the nucleus of the sodium, it's going to be more difficult to remove. It's also, the 1s electrons are more difficult to remove because of the shielding of some of the others. So as you look, as there's more shielding, so as we go down the periodic table to scandium there, and scandium is actually a 3D element, but notice because there's more shielding, the 1s requires so much more ionization energy to pull away. Now, when we look at ionization energies as a trend, we're more so looking at the ionization energy of those valence electrons, of the outermost electrons. And basically, that's what you see over here in the 3s and the 3p and even the 4s. So I just want you to recognize here, like, the vast 433 megajoules per mole. That's very, very difficult to remove a 1s electron from scandium. Okay, I want you to understand that. And I want you to understand why too. That is why electrons are lost and gained through the valence electrons because they can't be, it's so much energy to lose from those core electrons. So let's take a look at the output of this. So usually this photoelectron spectrum, this is what you'd call that, and it's spit out of a computer. And so what I want you to see is you have to look at the peaks, and you're looking at the relative size of the peaks. And so what you do is you start and you find the highest energy. So you find the highest binding energy on your output, and this is where your nucleus would be, is where the highest binding energy. So what you do is you work your way out. So here we have a 1s2, and we know it's 2 because there's more peaks after the 1s. So therefore we know that that 1s is filled. So now we go on and we're going on to another energy level. And so this next peak is the same height as the S from before, which was S2. So now this next peak is 2S2. Now notice that peak right next to the 2S2, and you can assume that's going to be in the same energy level. So that's going to be a 2P. However, that's not going to be a 2P6. What you have to do is, now that you realize that basically in relative amounts here, you see that each of these peaks on this represents 2 electrons. So you notice for every 2 lines that represents 1 electron. So therefore, instead of being like a 2p6, we've only represented 2 electrons, so we're at a 2p2. So now you take a look at your electron configuration, and you have 1s2, 2s2, 2p2. So you have 6 electrons represented. So we know for a fact that this is carbon. This is the PES, or the photoelectron spectrum for carbon. So taking a look at this one. Now I know that peak is a little bit skinnier. You're going to see sometimes skinny little peaks. Sometimes you'll see wider peaks. There are reasons for that depending upon what kind of equipment you're using, how far they are from the nucleus. As those peaks get further and further from the nucleus, they tend to get a little wider as they get really close, because the binding energy is very, very specific right here. So again, we find our binding energy, that's the highest, and this is where we start. So basically this is our nucleus. So we start at 1s2. Now we see that it's 1s2 because there's peaks after it. And so every 2 lines must equal an electron. So then we come down here and we have 2s2 because we fill the 2s energy level, and it represents 4 lines, which we know that every 2 lines represents an electron. So now we go here to the 2p. So there's an electron, there's an electron, there's an electron, and there's an electron. So we have 1, 2, 3, 4. So this peak is a 2p4. And you can also see that it's doubled. It's double in size from a 2s2. So there must be 4 electrons instead of 2. So I look at my periodic table and I have 1s2, 2s2, 2p4. I have 8 electrons, so I must have oxygen here. Looking at another one, this is just another way you might see it, where the peaks are just not as pronounced, and you're also going to see them sometimes where you don't see the lines. So you really have to use your relative, and you have to kind of figure out how far you're going here. So again, you're going to find your highest binding energy, which here's 500, so that must be your nucleus here. So here's your peak at 1s2, and you keep going. Down here you have 2s2. And then it looks like this is doubled the size of 2s2, so therefore you have 4 electrons. So this is another representation of oxygen because there's 8 electrons present. And here's another one where we take a look at, and it's a little bit bigger. So again, you find the binding energy. And notice now also, as the electron's getting bigger, notice that the binding energy, we start down here at 1,000. So we have a binding energy here. So we're looking at 2 lines equaling 1s2. So 2 lines. So it looks like every line now is an electron. So we have 2s2, then we have 1, 2, 3, 4, 5, 6. So this must be a 2p6, and we know it's probably filled since we have more peaks beyond that. So we have a 3s2, and we know that each line is 1 electron, and we go up 3 lines, so this must be a 3p3. So therefore, we've got 1s2, 2s2, 2p6, 3s2, 3p3. So we have 4, 10, 12, 15 electrons. And so we look on the periodic table to see what is 15 electrons. And that's the identity of our atom. So this honestly is easier than what it ever sounds like. As long as you know electron configuration, you can definitely figure this out. I do want you to understand, though, that because of photoelectron spectroscopy, now that is really how we took the Bohr model to the next level, is through photoelectron spectroscopy. So with the shell model, so when we say the shell model, it's more like the Bohr model, states that all electrons within a given shell are at the same energy level. Photoelectron spectroscopy data shows us that there are 2 subshells in N2 and 3 sublevels in N3. What that means is in N2, there's a 2s and there's a 2p. In N3, there's a 3s, there's a 3p, and there's also a 3d. So that is one of the reasons why we've actually, as scientists, gone to the quantum mechanical model, where it's not just pretty little orbital shells, even though that's kind of an easy way to, predict and explain and so forth. But the quantum mechanical model, again, is the SP, D, and F. And so we can look at regions where those electrons spend 90% of their time instead. All right, you guys got this. This isn't too bad at all, and I will hopefully see you tomorrow. Take care. Bye-bye.